Hey, welcome back, everyone. Happy to welcome you to this evening's episode again. Sabrina will be our presenter today. Welcome, Sabrina.
Hey, yeah, happy to be here.
I hope so.
Oh, I am.
Wonderful. So we had some exchanges before today, and I'll just ask her where she's located at the moment, because I think from the studies you're usually in Maryland and Baltimore, right?
Yeah, that's right. Baltimore, Maryland.
But New York today. Awesome.
Yes, New York. Maybe someday I will move here. It'll be great. We'll
okay.
see.
Shall we keep the fingers crossed that this will happen, or?
I hope so. Please do.
Okay, I will. So yeah, really happy to have you here as a speaker. So wonderful. For everyone who just joined, just an organizational thing before we really start. As you know, we are open to questions throughout the presentation. You can ask a question at any time. For that, you will find a Q&A button here or here, and in the navigation bar, depends on where it is on your screen. Fill in your questions in Q&A, and I will take care of everything. And we'll take care that we will ask you questions and that we will be answered. I'm sure Sabrina is more than happy to answer them. Yeah, okay, that's good. Yeah, so for me, just to give you a short background, I actually met Sabrina virtually, of course, on Twitter. So this is the first time on Twitter. Usually it's some mix-up between LinkedIn and whatever. But this time it was Twitter. And it just got stuck with kind of language and language model thing you're working on. So is it just fun part, or is it doing part of your academic research?
It's really part of my academic research. So I'm doing a PhD in Baltimore on things that have to do with language modeling. It is a little bit all over the place, but language modeling is like the red thread that kind of goes through a lot of the work that I've done there. Yeah.
Ah, interesting. So what are you interested in regarding what is really your research?
My real interest, like the most focused thing, is trying to have language models or any kind of NLP models learn the granularity of their input, learn what is appropriate tokenization, what are the units, do they have embeddings, what do the embeddings look like? So really I'm fascinated by the idea of learning these latent discrete units, latent underlying things from data. Mm-hmm. That's what I'm
Is there a specific reason you have been, you got fascinated with natural language processing, or is it just like, yep, okay, it happened?
I think I've always been super fascinated by a language, specifically other languages. Like I remember very distinctly, as like a little kid, we were going to like a vacation in Bulgaria, and I was like, oh, I'll just be prepared. I'll just transliterate the alphabet. I'll just figure out the Cyrillic alphabet and the Latin alphabet, and then I can understand everything, right?
Yeah, yeah.
And I was very disappointed to find out this was not the case. I could not at all understand Bulgarian. Yeah. So yeah, it's always been an interest of me. And that kind of nicely came together when I started studying computer science. So that's how I got into NLP.
Oh, cool. Awesome. Yeah, I personally, I'm just also very interested in languages and the differences regarding cultures and cultural expression in language. This is a part of a little bit what we are doing. I was just fascinated by a story I heard a few years ago. It was about translation of Hemingway, a translation from Hemingway from American English into Japanese. And the test was, what happens if you translate it back from Japanese into the English again? And can you still keep the kind of style, the atmosphere of the text, or is it just gone because it's too technical to like a robot, right? Robot talk. And it was really fascinating because this is one of the tests usually make also with students to say, do you think this was written by machine, text A, or was B the text? And it's fascinating where we are today. But no, it's really your story. So I'm really looking for today. What is the subject we're talking about today?
Yeah, we're going to be talking about a sort of number of things, but what I'm going to start with and what's probably going to be most of the time is talking about trying to actually do some comparisons between languages.
Yeah.
So figuring out our NLP models, do they work on English? I mean, okay, that's reasonable, but do they work on other languages? Do they work on German? Do they work on Mandarin Chinese? Do they work on, all sorts of languages? And that's sort of where we're going to be starting off, discussing how can we measure how well things work on a language? How can we actually fairly compare that? Can we find some interesting trends? Like, do some languages are they intrinsically harder maybe? And then we'll go from that to talking about translations. So we'll actually go right into this question that you posed, like, oh, is this different because it was translated in this case by a human?
Yes.
As opposed to being the original. So we'll take a look at that question, how translated text compares to normal text. And then we'll dive into the translation process a bit and figure out, what is actually happening in translation? Can we use some of the methodology that we used in that first part to make some interesting statements about translation?
That sounds cool. I'm one of those guys who just start reading books from the end, right? I need to know the end before the beginning. So just a quick question here. Do you think we can be optimistic that language models really work pretty well with languages? Or it's just like,
I think there's a lot of in there. That said, things worked better than I thought they would.
Okay.
So I think language modeling as a task is simple enough in theory that we don't have too much of a difference between languages. It's still very much measurable. I'm going to give that much away. But I think other tasks would probably show larger differences.
Okay, cool.
Yeah,
so please take the floor. It's yours.
All right. Let me share.
One thing before we start. So sorry, that's good. Start, but don't start. I have a quick poll for you guys. I would like to, it will help us, right? It's always good to have a little bit background of what kind of job you're doing. So it's much easier to focus on things. And it's much easier for us also to learn what makes sense today. Again, also feel invited to ask your questions. Don't think there's a silly question. There's just the only silly thing you can do is not to ask if you have a question. So we're really happy to answer.
Yeah, questions are the most fun part of these talks, in my opinion. So definitely go for it.
Yeah.
Okay, cool. So with this abstract already out of the way, I think we can jump right into it and go start with our very first question. Are languages equally hard to model? And like we talked about in our little preamble, we're going to be talking about language modeling for a lot of this task. So I don't know how familiar you are with language modeling, but here's sort of a brief introduction to the whole topic. What we want to do in language modeling is have a NLP model tell us how likely certain text is to appear. So give us a probability for some snippet of text. In this case, if we have like this partial sentence, I just didn't want to write it all out because space is expensive. The cat chased you can imagine how this goes on. How do we get the probability of a sentence? The usual way to do it is to decompose this probability using chain rule of probability into just predicting each word at a time. So you start out with the probability of the, okay, that's probably pretty high. The probability that the word cat happens after you've already generated the word the probability that chased happens after you've already generated the and cat, and so on. And these are probability distributions that are always just over your vocabulary. So they're always just over this list of items that you have, the list of types, in this case, something like words. So we can express those relatively easily. It's just an AI classification task, right? We're classifying what is the next word given the previous words. And that's how we can get the probability for an entire sentence. Now, of course, we can also, and I'm going to show this in a second, we can also see this generative story as a generative model, as a model that can generate text. So how are we going to do that? Well, I'm going to make things a little bit more interesting and tell you a little bit about how this classification works. Naturally, we use neural networks, and specifically every one of our words in our inventory is going to get assigned an embedding, a real valued vector that serves to represent this word, its meaning, its usage, something like that. And then what we do is take our favorite recurrent neural network. I know nobody uses RNNs anymore. These slides are a few years old at that time. When I started my PhD, we still did RNNs. But you can imagine this also being a transformer, if you like. Point is, you perform this classification with your RNN or transformer cell, and then pick an embedding in this classification process, and ta-da, you've generated a word. You feed it back in, do the same thing again, this time having seen you generate the next word, and so on. One thing that I want to, that you should be wondering, I should say, is, well, this is all nice, but what is in our lexicon? What is our list of words? What do we do with words that aren't in there? Like maybe sometimes we want to generate or assign a probability to a word that we've never seen before. How are we going to do that if the classification only goes over entries in the vocabulary, right? It's a difficult question, and the obvious answer for many decades in NLP was to say, look, if it's really that rare, it probably doesn't matter. Let's just replace all those words with the token unc for unknown, and that's fine. And so if you want to generate text, maybe it's going to have some of these unc tokens in it. That's fine, whatever, we don't care. Of course, fast forward to current day where natural language text generation is actually something we do all the time. We do care, unfortunately. We kind of want these words because they're often really useful, and nobody would like, what are you going to do with text that has unk in it, right? We don't know what to do with that. So what we're going to be doing instead is maybe something like this, where we have our model not generate one word at a time, but generate one character at a time. Now that works out, okay, because the set of characters we can assume is closed. We can just take all of Unicode if you really want to, and then everything works out fine. But that's kind of a nasty solution in that there's really a lot of computation we're doing here. So many RNN cells, and now the next word to be spelled out is T and H and then E, and it's just like, okay, why are we spelling this out again? We should have just memorized this, right? So character level models, not perfect. They solve the issue of unknown words for us, but they're not perfect. Out of curiosity, does anyone know what the currently predominant paradigm of being what is called open vocabulary, so being able to explain all possible strings and words, how we achieve that generally in NLP these days?
No.
You can post it in the chat if you know. Just curious if someone.
Anyone an answer? Please reply. You can use the chat if you like. Just ask. Yeah, token-based tokenization, JSD.
Yes. So that's the idea. We are using subword units. That's what we call them. Something like if you've heard of BPE or Unigram LM or sentence piece, which does both of these things, then that's the kind of idea that we're doing. So we're not taking entire words necessarily, but we're taking pieces of words. And sometimes that can be very segmented, like your example of chase. But sometimes they are just the entire word. Like the word THE, it's going to stay its own word. That's fine. But then words we've never seen before, we can now assemble from these little building blocks. Yeah, so that's what we do these days. Fun fact. You could give a whole talk about that topic too, but I will forego that. So that's the basic gist of language modeling. We want to have a model that can assign a probability to text, or alternatively, we can say a model from which we can sample text. Any questions on that? I mean, I hope that you would ask them in the chat if you have them, but just in case you want the extra reminder. Otherwise,
okay, but it's fine at the moment.
Cool. Otherwise, yeah, let's jump into our main question from the first part of this talk. What kind of language is hard to language model? This was a paper we had at ACL 2019. And I want to start it off by giving some questions and answers about this work. So first of all, do current language models work equally well on all languages? And I kind of gave away the answer, no, they do not. Which one do they struggle with more, German or English? Maybe you have some idea of what it's going to be. And the answer is perhaps not too surprising. German seems to be harder for these models. And those two questions are kind of questions that we had already teased in a previous paper of ours. So this is going to focus on some new questions instead. What about languages that are far outside the Indo-European range, let's say Mandarin Chinese? Well, the answer will be it depends. We'll see what it depends on.
We have one command which is saying Korean, right?
Oh, I don't actually know if we have Korean in our data. Let's keep an eye out for that one. That will be interesting to see. Yeah, so what we wanted to know in this work is, first of all, can we reproduce this effect we've seen before? There are differences in performance, so I'll go into that. But we also wanted to see maybe there's some unifying characteristic of languages that makes them harder or easier to model. And it turns out, well, it'll be kind of disappointing, but we'll see about that. And finally, is translationese easier? So translationese being sort of this dialect of a language that translators have written in response to an original document that was written in a different language. Is this markedly easier, perhaps more robotic, or harder because you have this whole interference from the source language in there? And we'll find out it's different, but it's not actually easier. So let's just jump into it. What do we need to do? Well, we first need to define difficulty. How do we measure that? Then we take a look at the models and the languages that we compare on, do our little study about, is there some correlations here, and talk about translations. So how do we measure difficulty? Well, as I said, we're going to want to use language models, and the language model assigns a probability to a string. So this string, I love Florence, might have a probability of 0.03. And oftentimes we want to talk about these probabilities in terms of information content, or alternatively, we can say surprisal. And if you've ever coded up any kind of NLP like neural nets, you will have seen your NLL, your negative log likelihood. That's exactly what this is. That's exactly what we're measuring. Okay, so this sentence would have 5 bits of information, we could say, under this probability distribution that assigns it 3% probability. We do this German sentence, and now this has a lower probability and therefore more information. It's more surprising. It has, say, 7 bits, and we can look at this Dutch sentence, and we get something like that. And now we just compare the bits, and ta-da, we're done, right? Well, not really. I mean, we can't compare these 3 sentences because they all talk about very different things and very different style with different length. It wouldn't be fair to compare the probability distributions on those, right? So first of all, what we need to do is make sure that anything we're measuring happens on a fair playing ground of data. And so what we're going to be using is translations. Now, if we have these 3 languages all say the same thing, resumption of the session, the Europower fans among us will notice this little phrase. Now this is a fine thing to do. Now we ask an English language model, what's the likelihood of this string? A German language model, what is the likelihood of this string? And a Dutch language model, what is the likelihood of this string? All in their respective languages. And so we get these bits, and we should expect that the information content in these three sentences should be more or less the same, right? Because they're kind of saying the same thing, and it shouldn't be any more likely to say resumption of the session in English than it should be in German. I mean, I'm assuming we all have enough parliamentarians in our ranks, right? So we should expect these numbers to end up close to one another, but importantly, they might not end up exactly the same. And that's because the probability distribution is in the end just an NLP model. It's a model that's imperfect. It's a model that assigns probability to some things that are not actually grammatical, and then assigns too low a probability on the things that we do see that are grammatical. And so that's what we're going to be measuring. If a language model is a poorly trained language model, a language model that struggles with a language, then it's going to assign these correct answers, these gold strings, relatively low probability, because it's wasted all its probability elsewhere, or because it thinks that they're not actually correct. And so the lower probability it assigns, the worse a job it did. Okay. And so if we measure this in bits, we see they're all kind of the same, but in this case, the English example had more bits, so the model was more surprised to see this sentence. The German one was not very surprised. And yes, Alexander pointed out, I completely messed that up. I've given this talk so many times and I've never noticed. That's right. If we look at the probabilities, the English one is more likely, so it should be less surprised. The German one is less likely, so it should be more surprised. So flip those two numbers in your head. I never noticed that. That's amazing. Thank you for that one. Okay, that's sort of the setup that we're going to be going for. We're going to be measuring these surprisals, these probabilities, and then compare which model had a harder time than another. As I said, we are really interested in what kind of data can we use for this. And so since we need translations, both for training our language models, so that we make sure they're all trained on kind of the same data, they're all trained on the same ratio of resumption of the sessions, and then tested on translations. And testing is what this up here is supposed to represent, where we take a bunch of sentences and then ask, what are the surprisals? So we get our languages from the European Parliament corpus. That gets us 21 languages that share about 40 million characters worth of text. And we also add to this data from the Bible, where we take 62 languages that gets us a fully parallel set between all of them that is about 4 million characters in size, which really isn't much, but we're going to make do with it. Okay. Now, if you are familiar with some multilingual research and you've seen how many Bibles there are, you're going to be like, what, 62? I've seen more than that. The answer is yes. There are data sets that contain hundreds of Bibles. However, oftentimes the Bible in these data sets is only the New Testament. So that is useful, but that will make it even smaller. So we kind of have this interesting trade-off that like the more languages we want, the smaller our data set gets. And the bigger our data set we want, the fewer languages we can include. So we cast this as an integer linear program, which is super fun and a giant tangent, but anyway. And then solve this with Gurobi, and we end up with 62 languages that share 4 million characters as solution for biggest overlap. Cool. Okay, so we end up with 69 languages. This was not on purpose, I promise, from 13 language families in total. And with that, we can do our experiments. Now, this is the one caveat, the data. The second caveat is we can only compare our perplexities, our probabilities, our surprisals if we use the total bits of an open vocabulary model. Okay, now why is that? Let's first talk about the open vocabulary part. What would happen if I choose a model that had unks in it, that had this unknown token? Well, it would kind of be cheating, right? If I need to tell you, if I need to generate text, then I generate oh, unknown word, I shouldn't get full points because like I didn't predict the word, right? So if we would imagine that there are some languages that have lots of unknown words, perhaps due to morphology or some other phenomena that mean that we have many word types, they would just produce unk all the time and get away with it. They would just have way too good performance. So that's unfair. Everybody needs to explain every part of the string. There is no cop-out with unks. That's one thing. The other thing is we need to look at the total bits, the total probability of the entire sentence. We cannot look at the probabilities per word or per character. So what we often call perplexity, right? The exponentiated probability, essentially. We can't do that. Why can't we do that? Well, here's an example. It's like the word putsch in Czech and German, same word, essentially. In English, it's a coup. And we should assume that if both speakers like to talk about coups equally likely, then this word should appear equally likely. And so they should be equally difficult. However, if you were to normalize per character, well, the Czech one has a lot of information in each character, and the German one doesn't have a lot of information in each character, because by the time you see T and S, well, you know it's going to be C and H next. Okay, so that will be sort of unfairly advantaging languages that tend to use lots of characters to express the same thing. So we really need to look at the total probability of the entire sentence. So really at the probability of the complete utterance, regardless of how it was predicted, whether it was predicted character by character or word piece by word piece, doesn't matter. Just give me the total probability of this item. Okay. So that's what we're going to be doing. Let's go. Essentially, if we take a matrix of sentences like this, 3 languages, English, German, Bulgarian, 4 sentences shown, we call this aligned multi-text, but essentially a fully parallel corpus. That's our test set. Well, we run our language models, as I said, and now we get these surprisals, these information contents for every one of those sentences in every one of those languages, right? The first column is given by an English language model, the second one by a German language model, the third one by a Bulgarian language model. Now, the color is supposed to indicate how much information, how much information there is, how much surprisal there is. So we see that the third sentence is pretty high density, so maybe it's a very long sentence. And we can kind of make out with the naked eye that German seems to be a bit harder than English and Bulgarian, something like that, right? And what we can obviously do is just sum up all of these surprisals, the sum of a bunch of information content of a bunch of bits, that's information content again. So we end up with a bunch of bits for English, some for German, some for Bulgarian, and now we can just compare. Who has more bits? Who had more trouble predicting what was going to happen? Who was thus worse trained? And that's all fine, but we wanted to make our life a little harder. And we're going to see only in like 10, 20 minutes why we made our life harder. But for now, bear with me. Imagine your sentence matrix had holes. Imagine there were some sentences that you didn't have translations in all languages, but only some languages, maybe only one other language. How could you do this now? Well, we can still run our language models, of course, and they will still give us the same scores for all these sentences. But now we couldn't add them up anymore, right? Because if we add them up, then German and Bulgarian are going to be unfairly punished just because they happen to contain a translation for this hard sentence. English just didn't translate it and so gets away easy? No, that would be unfair. So we can't just sum up things or average things anymore. What we got to do instead is build a probabilistic model that can deal with missing data. And we posit one such model by saying that we want to explain this surprisal, this information content for each of those cells as essentially a product of the intrinsic length of that sentence, or like maybe not length, but like information content, like how much is in there? How hard is this for all languages? And then a factor that indicates the difficulty of a given language. Specifically, we say that it's supposed to be this product of these exponentiated factors times this length. And we say that this is just some log normal noise, just put a probability model on that. And now we can perform inference in this. We can try to learn or get distributions over these intrinsic sentence densities and the language difficulty factors. And so that's what we're going to be doing. So given this matrix of surprisals, we now have, through this equation, a way to give us estimates for these things that we're really interested in. Okay. Now, I kind of lied because this model is a little bit simple. We actually use a more complicated model. It's heteroscedastic. I learned that word through this project, and now I see it everywhere. But I'm not going to go into detail for these slides. For the purpose of what we're doing, this is reasonable. Sorry?
This sounds like a pretty crazy word. Can you show it again?
Essentially, the idea in the heteroscedasticity is that we're saying we have unequal variance. So the non-heteroscedastic, the homoscedastic model is this one. It assumes equal variance. Or like variance to scale just with n, which is not what we want. The variance of this log normalized distribution, sorry, I should have said that, which is not what we want, because really, if we have a very dense sentence, things should kind of even out. So we instead have a model that is trying to follow this intuition of longer sentences, kind of having averaged out effects that lead to sharper estimates. So our standard deviation is no longer a single static factor, but is now also given by something that includes the length of the sentence. Yeah, that's how this model is different. But you can check out the paper if you're interested in that. It's actually explained there as opposed to just vomited out on a slide like here. Okay, now you're going to be like, oh, this is really cool. I bet it really makes a big difference. And let me tell you, let's just deviate from the conference slide for a bit to be a little honest. It really doesn't matter. We also try to be cool and Bayesian, be like, yeah, what kind of distribution should we use? Is it a log normal noise distribution? Maybe a gamma noise distribution? Should we put a prior on it? What kind of prior? And we try to be like, okay, well, maybe we don't want point estimates. We don't want the map estimate for the language difficulty coefficients. We want the whole distribution. So we can do Hamiltonian Monte Carlo with Stan and fancy gradient-based MC-empty methods. And it takes many hours and it's very unstable, but maybe it's useful. And the answer is no. It just led to a lot of misery. If you really have this full data like we did, and you don't have like lots of holes, you really don't need any of this. You don't need the heteroscedasticity. You don't need to be good Bayesian. You don't need to do actual marginal inference with HMC. You can just do the basic boring thing. In fact, if you really have the entirely full matrix of sentences, let me get back to that. If you really have this full matrix of sentences, all this complicated stuff that we built here gives us like 99 point something% the same answers as just summing them up and averaging them. So we really made our life very complicated here for, I'm not going to say no good reason. We all learned something and part of this will come in handy later, but man, I was furious when I found out that all the stuff that I'd done made no difference, but that's how it is in research. Cool. So we can put a check mark for difficulty. We know what we mean by difficulty. Let's look at the models and languages. So we're going to use a character level model, as I said. We're going to use a BPE based model. So using these words hacked up into pieces. So the word cat, for example, was cut up into cat, and then this glue marker and T. Chase was also cut up into 2 pieces. This is with few merges, where merges really means, it's kind of intuitive. Merges really, these two aren't merged, so we don't have many merges. If we say, okay, make a few more merges, then maybe cat isn't cut in half anymore, but chased still is. That's reasonable, right? So we have these models, they're all open vocabulary, they can all explain all possible strings, but they probably differ in their performance, right? So one thing we got to ask ourselves first is, okay, well, what do we do here? Few merges, many merges, does it really matter? Like, what's the difference between these two models by themselves? And so let's take our 21 European Parliament languages and just compare. So this picture shows the performance. So the number of total bits of the corpus, where lower is better, as we've said, right? Because the model is less surprised, as a function of how many merges there are, how heavily merged is this language. And I say this is a ratio because I use the number of merges divided by the number of types if you didn't hack the words into pieces. I figured that was a reasonable thing to do, and it'll turn out to be a huge mistake, but we don't know yet why. This is a fine thing to do. And what we see is that languages kind of differ in how they work. So at the very top, we have Hungarian, really hard to model apparently, and it gets better and better if you have some merges. But then if you keep merging, it gets worse again. So Hungarian actually likes being chopped up into little pieces. That's interesting. Other languages like, let's see, Italian, the red one here, yeah, it kind of gets better if you merge more. There's a little bit of noise, but the more you merge, the better, essentially, right? Or English, this black line down here. Yeah, I mean, the more you merge, the better, more or less. We already see the ranking kind of, right? You can see Hungarian and German are pretty hard. English, Slovenian, and Danish are pretty easy. But you know, let's look at that in detail on the next slide. Okay, for now you might be like, okay, well then that's kind of messy. Which model do we choose in this case? And if you just average them, yeah, it kind of turns out that 40% is generally good for all of them. It's not always optimal, but it's pretty good. So that's what we're going to be doing. And you see that tuning the merges for each languages individually versus just taking this 0.4 ratio for the language without tuning, it does make some difference in the ranking, but the difference is much smaller than the difference between these BPE-based models and the character-based model. So for the purposes of the remainder of this talk, we're just going to look at this 0.4 ratio model just to keep things simple. Okay, so let's zoom in on this little bit and actually look at our ranking. We're going to show in this plot of the difficulty, so these coefficients of a probabilistic model that we derived. On the x-axis, it's going to be the difficulty using the BPE model, the model with the word pieces. And on the y-axis, the difficulty with a character level model. So if you put in the diagonal, it separates the space into easier with BPE and easier with characters. Let's put in the languages. We say that German is one of the hardest languages, both for the both for the character level model and for the BPE level model. English down here is relatively easy, works pretty well with the character level model, apparently. And, you know, a bunch of other things all throughout. Interestingly, Hungarian is pretty hard, but Finnish turned out to be fairly easy. That was kind of weird because in previous work, we've shown that Finnish was kind of hard. So goes to show some of the noise in this, I guess, and how maybe the model we used in the older work was just not right good. But overall, we see that kind of cluster around the diagonal. That makes some sense. The performance is correlated between BPE and characters. Okay, so this is 21 European languages. We also said we wanted to use Bible languages, right? We said we had lots of Bible languages. Let's make this bigger. And before I do that, I want to show you this interesting result. On the right, we now have the difficulties using the Bible. And I've highlighted only German and English for now. Now, why are there multiple data points for German or for English? What do you think? Yeah, exactly. There are different translations of the Bible. So the Bible has been translated into German and English multiple times. And so now we can actually compare how much does a translator add to the original or take away from it or impact in general the modeling difficulty. And we see that there is quite some variance, right? The German translations aren't all equally hard. They differ greatly in their difficulty, right? Nevertheless, we can also see, and that's the positive takeaway, that even across all of these translations in German and in English, German is harder than English for these models. Like, that is still a very clear difference. And now I can put in all the other languages and things get a little bit more messy. Just one thing to see is the ranking between Europol and Bibles is reasonably stable-ish. German and Hungarian stay on top. Czech was not that easy before either. And like here, Lithuanian and English are near the bottom. So it's not a perfect match. And we get as much by seeing this. There is a lot of noise in this process, but there is some signal that remains. Okay, the one thing that I want to show, because I said it in the intro, Mandarin Chinese is very heavily in the easier with characters model, because with characters it has a very low difficulty, is in fact the easiest language. And with the BPE model, it's reasonably hard. Which makes sense because we want our pieces of prediction, our units of prediction to be reasonably large. And in Mandarin Chinese, well, Chinese characters certainly have a lot of meaning per character. So it makes sense that the character level model is stronger than it is for something that's written in, say, Latin alphabet. Okay. So that is sort of the main results slide. Lots of languages, lots of rankings. That's all nice. But is there anything we can take away from this? Anything interesting? Something that correlates with difficulty? Well, we thought first maybe morphology, right? Morphology makes languages harder, lots of inflections, lots of word forms, complicated agreement patterns. That can make things harder. But if we take these plots where on the x-axis we show just how many morphological categories there are in a language, and then plot the language's difficulties with the BPE level model on the left and the character level model on the right. And, you know, honestly, I don't see any correlation here. You know, previous work, we did see some correlation, but in this paper, honestly, I don't see any. So that's disappointing. Morphology is clearly not to blame. Well, what are we going to do about that? Especially because in 2018, we said that, hey, no, morphology is to blame because we found Finnish so hard. So I was like, hey, author of the previous paper, my numbers don't match yours. We got something different for Finnish. And can I reproduce this? Where is the code? And we just didn't have the code anymore. So that was really embarrassing. We did this paper together. This is like a paper I did when I first started grad school. And I never actually touched the code much. So nobody of us knew what the code was. Anyway, we just had to move on with it and pretend everything was fine. Let's look at some other motivated regressors, some other things that could correlate with difficulty. How about this morphology feature from the World Atlas of Language Structures? Nope, nothing. How about order of subject, object, verb? Nothing. How about the head-part speech entropy, which a paper had proposed just the year before, so that was sort of recent. Nope, nothing. And finally, this was a hypothesis one of our co-authors had. What about average dependency length? Average dependency length, the idea that since some words in a sentence are sort of related to one another, right? Like a subject and the verb, they might share grammatical agreement and those sorts of things. These dependencies can be arbitrarily long. They can be stuff in the middle. And some languages just have longer dependencies and others have shorter dependencies. Is there a correlation between this and difficulty? And the answer is yes, we did show correlation. And had it been the only thing we had tested, it would have been significant. But you got to be careful because we tested so many things, right? We tested our morphology feature, Wall's morphology, Wall's SVO, head-part speech entropy, And sure, if you run 50 significance tests, yeah, okay, one of them is going to show up positive. Fine. Now, what are you going to do? So correcting for the fact that we tested so many different correlations, it's no longer significant. So if you want to write a follow-up, maybe focus on this one. You might find something. Okay, overall, disappointing as hell. What we did find, well, okay, so again, goodbye conference slides. Hello to my private messages, messaging the professors like, hey, nothing interesting happens. All this work that we've done, there's nothing of interest here. And we've all seen this being left unread. And I was like, okay, what do we do? And the answer is very quickly, it'll be tricky because nobody likes a negative results paper. But what we're just going to do is we will attack our previous paper. So the previous paper said, hey, blah, 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 morphology is to blame. It's all very easy. And so we were like, well, these previous people, which you don't know are actually us, but these previous people, well, they said it was this way, but we show it is not this way. This is interesting and noteworthy. And indeed, the paper got in. And if you read the paper now, you will not find as aggressive a formulation. It will merely be reconciliatory, like, oh, well, they differ, but I'm sure they did their homework too. So if you ever want to publish a negative result, maybe that's how you do it. That's how we did it. And people liked it well enough. Anyway, for all this doom and gloom, we did find some correlations, like the fact that for the character level language model, just the raw sequence length in terms of characters, or put differently, just the number of prediction steps that you do in your left to right autoregressive model, does significantly impact the difficulty for both Europarl and the Bibles. So for the character level RNLM, it really does look like the Czech putsch is easier than the German putsch, which is interesting, but which also sort of makes sense because we've seen Mandarin Chinese, where characters have a lot of information, do really well in the character level model. So this makes some sense. The other thing that we also claim to have seen was that the raw vocabulary size, so just the number of types before we even started tokenizing and using BPE, impacts the difficulty after BPE. We were like, whoa, this is amazing. This is really interesting to see that even if we do BPE, we still have these issues. However, literally, as I stood up at the podium on ACL 2019 and presented this work, literally then I realized, hold on a minute, you might have messed something up here. Does someone see what I messed up here? Why is it not at all surprising that the number of types in the language before I apply BPE is still impacting difficulty, even though I have done BPE? It's sort of a tricky thing to see. The answer is because I said I use BPE 40%, right? So 40% of something with very many types, well, it's going to give me very many types after BPE too. Something that has fewer types, well, 40% of that is going to give me very few types as well. So it's actually not at all surprising that this shows up. It's a very expectable correlation. And well, I said as much, but God, that was a moment. Anyway, this was all really disappointing, right? So these were sort of the things in the paper that were following a recipe, going through the motions, but nothing really striking. And so that's why I really like this last bit that we're going to be looking at, and that is translationese really easier? The common assumption is that translationese is something that I have, I'm given a German document and I have to translate it into English. Well, my translation is going to look different than if I had just written the text in English to begin with. We want to know, well, is there some systematic difference? It's commonly assumed that these translations are easier than native text because you're kind of clinging to the structure that is given by something else. But is that true for models? Do they find it easier? Okay, how are we going to measure this? Well, the good thing is that the European Parliament corpus not only has all the translations of all the utterances, it also marks which one is native and which ones are translations. So what we can do is take our corpus with all our columns, the languages, and sort of split each column in half. So we have one column for original English and one column for German, for translated English from German, from Dutch, something maybe. One for original German, one for translated German, one for original Dutch, one for translated Dutch. And you see this matrix has lots of holes because you can never have a sentence that's both original and translated, right? So there's always going to be some holes. But we can make sure that we have at least some original and at least some translated sentences for each language. And now if we do that, we can just run our estimation procedure and look at the language difficulty coefficients for all these columns. One for English original, one for English translated, one for German original, one for German translated, and so on. And then we just compare the difficulty of original with the difficulty of translated, and voila, right? We get something out. What do we do? Oh, look at that. The original difficulty coefficient is higher. The original languages do indeed seem harder. Oh, but we missed something. The way we did it so far, we missed something, and something crucial. Let's just recap what we did. We trained our models on, yes, parallel data. We trained an English model and a German model and a Dutch model, and they're all trained of translations of one another, right? And then we evaluated them on this matrix. What did we miss? Does someone see it? This is a really tricky one, and it only came to my mind like a week after I had written the other stuff down. So I'm not surprised if nobody sees it. The issue is that we have trained on mostly translationese data. If we train 21 models, then 20 of those models will be trained on the translation of the sentence that is native in the one other model's language. So even the language English, which has the most native utterances, so almost 20% of sentences are native in English. Even for English, the English model will have seen more translationese English than it has seen native English. And this is much stronger in effect with these languages that have fewer native sentences, right? So, okay, then this kind of explains it, right? If we train our language models on translationese and then we ask, oh, do you find translationese or original harder? Well, yes, they're going to find translationese easier because that's what they've been trained on. So we need to devise a different experiment. We need to change the training data, honestly. That's what we need to do. We need to balance the training data. And so what we're going to be doing is we're going to split this time only one column of our languages. So we still have one German, one Dutch, but we have one original English and one translated English for our training set and for our test set. And now we just delete sentences from it such that we have as many original sentences as we have translated sentences in the training set. And once we've done that, we can be sure that the language models that we've trained, they have no preference of translationese versus native. They've seen exactly the same amounts of both, okay? And now we test on our test set, which again looks like this, that we have one English original, one English translated, but only German and Dutch just as one language. And now we compare these two and we find that the difficulties are now actually the same. So what does this tell us? Well, it does tell us that translationese is not necessarily easier or harder to model, but in conjunction with our previous finding that they seemed harder if we trained on more translationese, that shows that they are actually different. There is a difference between translated and original text, and these models pick up on that difference, whether they like it or not. Which I thought was a really interesting conclusion, and which concludes this part of the talk. Takeaways: make sure your training data is comparable and fair. Working on translations can be a good way to do that. Just think of translationese. Make sure your metrics are comparable and fair. No unks, please. and make sure your stats are fair. Don't do p-hacking. It would have been easy to say like, oh, look, we found one correlation in 100, therefore it's real. But don't do that. It's very sad. I know. I was very disappointed. And I was like, damn, I wish we tested fewer things so it could be correlation. But that's life. We're going to do good science. And finally, of course, please, if you have the opportunity, work on more NLP resources for more languages. And that's it for this first part of the talk that I realize has taken up a lot of time because it went in a lot of detail. So yeah, I don't know where we are for time, how exactly is best to proceed.
I would say it's 20 past 7 here, so 50 minutes or so. Do you think you can make it?
Yeah, I could just I could talk about this evaluating translation models, or talk about chatbot calibration, or talk about tokenization. Anything, whichever people are interested in. I can, yeah. Or any of these things on the slides too, honestly. So if you have some. Yeah.
Others asking, are there cues in data statistics in the translation ease that made the difference?
That's a good question. I'm not sure how you would find them. It would be very interesting. I don't know any of such cues. Yeah.
Okay. So regarding the suggestion, any priority you would have yourself?
I don't really mind anything. Maybe you can just, I don't know how easy or hard it is to make a quick poll. Can I do that actually?
Not that fast, unfortunately.
Oh, I see.
Just repeat it. Say one is, what was the first one? So the next one would be?
We could just keep going with the translation models because it kind of fits nicely.
Okay. Second?
Oh, okay. Translation models, chatbot calibration.
Chatbot calibration, okay.
And tokenization.
Tokenization. Okay, guys. Question to the audience. We have three options to finalize the presentation. What kind of thing would be interesting for you? Just proceed with what we did now. Second was, what was it?
Chatbot calibration.
Calibration, or the third one was tokenization. Say 1, 2, 3. So we have one suggestion already. It's 2.
Chat vote coming.
Anyone else? Please vote. Quick vote. Otherwise, we go for the choice we have, right?
Oh, I will go with the vote. Let me open that up.
Good. So if no one else, 2. We have second 2, so we have 2, 2. 2 votes for 2. Okay. Let's go for the chatbot. Oh, we have all 1 3. Okay, 2 to 1.
Oh, it's exciting, but it's too late.
It's too late. It's after the clock went down.
There we go. Cool. Okay.
Thanks, guys.
Yes. So this is going to be a complete switch of topics. This is work that I did at Facebook AI 2 years ago or so, 2020. We were talking about chatbots, and it's like, God, finally she's talking about something other than language models. But, you know, in a sense, a chatbot that is generating text is also just a language model. So I feel fine doing this. So what we're going to be doing in this project is look at an existing chatbot that's really made for kind of chit chat, just something fun to interact with, and zoom in on one particular phenomenon. So if you take this giant chatbot, 3 billion parameters, solid model, really fun to talk to, honestly. If you have the GPU to spare, absolutely go download one of these chatbots and knock yourself out. It's really fun. But you can ask it something like this question: which is heavier, 1 kilogram of feathers or 1 kilogram of stone? I don't know. I got asked that question a lot as a kid by my father, and I always fell for it. And unfortunately, this chatbot also falls for this question, and it says feathers because they're heavier than a kilogram. Okay, this answer doesn't really make any sense, right? Which is kind of stupid. Like, this is very confidently said, and yet it is so wrong. And we find that this actually happens a lot, where the chatbot answers a question more confidently than it should. So what we do is we take a question answering data set, so like some trivia data set, trivia QA, and we ask our bot, our chatbot, the questions in this data set and look at the answers that it provides. We say the answers fall into 4 categories. It could be completely evasive, not even acknowledging the question. It could openly say, I don't know, not going to answer. It could try to answer and be like, I'm not sure, but I think it's this one. Or it could be really confident and be like, this is the answer. Like it has been here with the feathers in the stone. For each of those 4 categories of answers, we can also see, did it get the answer right or did it get it wrong? And so when we put that in, we have, this is just how much these categories occur. So it usually acknowledges the question only in 2% of cases did it not acknowledge the question. But it's like kind of nicely split across these 3 buckets. And if we look at the correctness, then we see that if it says, I don't know, then yeah, it's 0.3% correct. If it says, I'm going to try, it's at least 2.3% correct. And if it says confidently, this is the answer, that answer is correct in about 14% of cases. 14% of cases. Wow, that's bad, right? Like, this is really bad. 14%. If you answer confidently, you would hope to be better than 14%. No quiz show, no human quiz show participant is going to confidently say, oh, I know the answer, and then only be correct 14% of the time. Or at least they wouldn't last for long on a quiz show, right? So the problem is that the chatbot, just like humans, is overconfident. So we can say this is really an instance of a general pattern of poor calibration. Now, what did calibration mean? Someone know? You can put it in the chat if you do.
I think they're listening.
Okay. So we're going to say calibration is defined as certainty and correctness going hand in hand. So perfect calibration would be you are about as certain in your answer as your answer is likely to be correct. So the more certain you are, the higher the chance you're going to be correct. And if you're very uncertain, it's a very low chance of being correct. That would be perfect calibration. And it's something that's highly desirable, right? We want our models, our AI models, to give us estimates of their uncertainty. And we want them to tell us if the answer is maybe the best guess they can do, but still a guess, we would like to know that that's a guess, right? And so we're really interested in the certainty of an answer that is being output by a model sort of certainty, uncertainty estimation, being well calibrated. We want it to go hand in hand with the chance of correctness, right? And in this work, we are particularly looking at what we call linguistic calibration, where we want to say that the linguistic certainty, so the certainty that is expressed using natural language in the sentence, where the chatbot literally says, I don't know, but I think that, so and so. Or where it literally says, that's easy. That is this answer. We want those markers to correspond well to the chance of being correct, right? And we've already seen 14% correct in things that were linguistically marked as certain by human annotators. That's pretty bad. That's not great calibration. Okay.
Yeah.
So the question is, can we do better? Is there a way we can do better? Because if the model just doesn't have a sense of certainty, doesn't have a sense of uncertainty, yeah, well, then in that case, there's nothing we can do, right? I mean, it's just bad. But what if it does? What if the model actually has a sense of certainty and just fails to express it linguistically? What if that's the issue? And so let's first try to achieve probabilistic calibration. So the original definition of calibration, we want to predict how likely it is that the answer will be correct. How do we do that? Well, we take our chatbot, given a question, produces the usually linguistically overconfident answer. and now perform some sort of metacognition, if we want to put a fancy word on it, on the inside of the robot. Specifically, we implement a little calibrator probe, we should say. It's a probabilistic classifier that, given the question and the original answer, as well as the model's internal representation, the chatbot model's internal representation, tries to predict how correct something is going to be. So it's just a logistic regression, essentially. And we try to predict how correct is something going to be. And now in this plot, we're going to see the answers to that question. We're going to be seeing on the x-axis the output of this magical calibrator probe, of this magic ball that's supposed to tell us how likely our answer is to be correct. And then on the y-axis, we're going to show how correct was the answer. So this works in, like, we bin the questions, we put lots of questions in one bin, sorted by the output of our magic calibrator module, and then see how many of those questions were correct to get the y-axis value. And what we see is this beautiful correlation. We see that indeed things that have a low probability of a low prediction of being right, so where our magic calibrator module, given question answer and model internals, said, you're not going to get this one right. No, I don't think so. Indeed, we did not get these right. And where the model says, oh, there's a pretty good chance you're going to get these right. I think you're going to get these right. I think these are the right answers. They indeed ended up correct, or at least mostly correct. So this was really, really encouraging, right? So we actually have a signal to go on that tells us, that gives us a sense of whether an answer is going to be correct or not. So now all that's left is to say, what are we going to do with this knowledge? What do we do with the fact that the chatbot should know better? We intervene on the answer generation. What we're doing is we say, given our prediction, we classify this as one of these three things, either I don't know, try to answer, or answer confidently. And then we have a controllable chatbot that uses controllable generation, fine-tuned from the original. It's kind of a bit involved, and I'm not going to go into it, but we did fine-tune this chatbot to make sense of these extra categories so that now we can give it a question and give it the appropriate certainty that we would like it to generate in. And it indeed gives us an answer that more or less still contains the same content, but now expresses this with a linguistic certainty that is indicated by one of these three things. That's the idea. Now, does it work well? Depends on how you see it. I think yes, it works quite well, considering we didn't know if it would work at all. That said, the gain that we get is here, right? So we were looking at, again, the question answer pairs that were answered confidently. And we want to know how many of them are correct. The vanilla model got 14% correct, if you remember that. And our calibrated controlled model gets 39% correct. Now, how does it do that? The answer is it didn't suddenly grow smarter. It just doesn't express so much confidence for the most part. It now tries to be very hedgy and very uncertain about all the questions, as opposed to being super confident. And that's why the questions that it remains confident on are the questions that it actually seems to know better. So that's how this works. We did not make the chatbot smarter. We did not teach it new knowledge. We only made sure that unless it was really sure of its answer, it was going to be a little bit more hedgy, a little bit more uncertain. And that's really what we did here. Now, the paper has a lot of more interesting information, some example questions, lots of other chatbots that we tested, some n-grams that correlate with correctness and certainty, and then a little bit more about automatic versus human annotation of all these properties. But you can check that out in the paper if you want, or you could wait. We're currently working on a revision that's got to be submitted one of these days, fingers crossed, and hopefully it's going to hit the archives soon, a month or two.
Paper anywhere?
I'm sorry?
Did you provide the link to the paper anywhere?
Yes, it is no longer my linked thing. Do I have the? Yeah, you can. Yeah, if you search for the title, you will find it. You will find the old revision that we have on archive. So definitely go check that out. We have a new revision that's like slightly better written, because peer review does actually help sometimes. Who knew? So that should be out in a month or two. But yeah, definitely, if you're interested, go check out the paper. And then maybe I think that's a good point to break.
Okay, cool. Thank you.
Yeah. I can't actually figure out how to stop sharing my screen. That's annoying. What if I unplug it?
Thank you. So any questions left from the audience? Anything we should answer? Fascinating research. What's next for you?
I'm really hoping to finish up some projects that we are doing right now. One of them on learning the vocabulary. So not doing it the BPE way, but trying to learn it with a downstream task. That's one thing that I'm really hope we can see come to fruition. And then one where we have a language model that actually has an infinite vocabulary. So we have word-based types, but infinitely many of them. And somehow we make sense of the infinity. That's what I'm really excited about, that I've been trying to get done for years. And I would love to see that one actually run before I finish my PhD. So we'll see.
When will the PhD be finished?
I'm hoping that'll be like this summer, this fall,
This
something
summer.
like that.
Okay.
Yeah.
And do you have already plans for what's next, or is it just like let's see?
Well, my hope is to find essentially like a 1-year postdoc like position in an industry lab, because I really did enjoy some of the internships I've had, and I would like to have some more spend some more time there. And then long term, I do really enjoy teaching.
Yeah.
So I'm hoping to maybe find a nice academic position in like some liberal arts school, something like that. Some teaching-based job. We will see what happens.
Is this something, so decision to say, okay, I will still remain in the US, or do you thought about moving to different countries?
Yeah, that's going to be an interesting question. I do for now enjoy living here. And I think there's just a lot of opportunities here, lots of places to be. In the long term, I could definitely see myself living other places as long as they are English speaking. That's really where it's at.
The English is important.
The English is kind of important. Like they have to have some decent English, because I've tried hard to learn other languages, and I don't think I'm gonna learn any more languages. It's like it's German and English, and that's gonna be it. And yeah, we'll see.
How much do you have to work on the math side of what you're doing? So do you work with a mathematician, or?
Really, the work that I'm doing is relatively applied, I would say. So there's not a whole lot of maths in there.
Yeah.
Like it doesn't get much messier than the heteroscedasticity stuff that I showed.
Okay.
So it's relatively straightforward as much as the math is concerned. It's really a lot of like, figuring out how to make things work algorithmically, efficiently, and then how to deal with your data and devise an experiment that actually shows what you would like to show. Which is sometimes really interesting. Like it's fairly straightforward if you're just comparing like performance, you want to make your number go up, fine. But sometimes really interesting things, I think, have to do with an interesting experimental design, like with the translationese example.
Okay. Yeah, Sabrina, definitely keep me posted when your PhD has been finished and what's next for you. It would be interesting to follow up.
Yeah, for sure. I'm having my fingers crossed it'll all work out.
Yeah, I do. Okay. Thanks again very much for just taking all the time you did today, and for this quite emotional, quite inspiring talk, I have to say. That was awesome. Thanks everyone who just joined today. I hope you stay safe. And we will see each other again next month for our next session. But now I wish you all a nice evening, a nice day. So it's daytime for you. It's evening here. And yeah, enjoy the time you have.